Okay, so I think we can start now. I welcome you to the week 8 tutorial of the course Introductory Organic Chemistry 1 conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. I am Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry at IIT Bombay, and here let us move ahead for the last tutorial for this course. So, till now we have gone through a lot of basic topics in the course Introductory Organic Chemistry 1. So, today we are going to solve a few questions on the topics alcohols, epoxides, and aromaticity, and we are going to apply all the basics that we learned in last 8 weeks course and tutorial. Okay, so let us move. I hope my slides are clearly visible. Okay, so here is the first question of today's tutorial. Choose the reagent and reactant that would produce 2-methyl 2-butanol as the major product. So this is a question on synthesis of alcohol. So you have to basically prepare this tertiary alcohol, and you are given three options. You just have to identify which option is going to give you this tertiary alcohol as a major product. So let us see, let us look at all the three reactions that are given to you. Then we will figure out the product and look at the correct option given. Okay. So this is the first reaction that is given to you. We are treating this ketone with ethyl magnesium bromide first. So what happens when we treat a ketone with with Grignard reagent? This Grignard reagent you can visualize as ethyl anion C2H5 minus and MgBr plus. So you have an anion and a cation here. So what happens? The anionic species of the Grignard reagent attacks at this nucleophilic carbon center. Okay, this carbon center in this ketone is highly electron deficient. So this anion will donate its electron pair to this nucleophilic center. So in turn you get ethyl linked at this carbon center, and simultaneously if you push the arrow towards the oxygen at first, you will get O minus at this oxygen. Okay, so you get ethyl here coming from the Grignard reagent and O minus here and single bond here. Okay. So second step is the simple workup step. So in the workup step, the O minus anion, whatever you obtained in the first step, is neutralized. So simply you get in this reaction this tertiary alcohol. That means we are getting 2-methyl 2-butanol. So 1, 2, 3, 4, 2-methyl 2-butanol in this reaction. Okay. So this was the first step. Let us now move to the this was the first reaction given. We are left with next two reactions. Okay, let us move to the second reaction now. You are given this methyl ethyl ketone, this time ethyl methyl ketone. Okay, so now you are treating it with methyl magnesium bromide. Similarly, just like the first reaction, you can visualize this methyl magnesium bromide as methyl anion and magnesium bromide cation. So the anionic species will attack on this nucleophilic carbon center and you get O minus at this oxygen. Okay, that is clear. And here also we are working the reaction, working up with ammonium chloride solution. Okay, so in the workup step, the O minus anion will pick up a proton from the system and you get a neutralized OH functional group here. So what you got? Ethyl here, methyl here and one new methyl here coming from methyl magnesium bromide, and here OH. That means again you got the same product in this reaction. Okay, just we are making a change in the Grignard reagent and a change in the starting material ketone structure. Okay, so that happened in the second reaction given. Let us now move to the third reaction given. Here we are taking an ester this time. Okay, till now we were reacting ketone, now we are taking an ester this time. So we are treating this ester with again a Grignard reagent, which is methyl magnesium bromide. What happens if we treat here also in ester also, this carbonyl carbon center is nucleophilic, so the methyl will come and attack on this carbon center, and what happens this time, you have this methoxy leaving group this time. Okay, in ketone what happened, the alkyl groups are not good leaving groups, so you cannot push the alkyls after attacking at the nucleophilic center, but this time you have a good leaving group attached at the carbonyl carbon. So what happens when the methyl anion attacks, this leaving group is knocked out, and in turn you get this ketone in the first step. And again this ketone now reacts with Grignard reagent, and the reaction mechanism will be the same as this reaction, second reaction, isn't it? Because this structure and this structure is definitely same, so you get at the end the same alcoholic product. So what we observed, just making a little changes in the starting material and the structure of the Grignard reagent being used, we synthesized the same alcohol as the major product. Okay, so what happened? All the three reactions given in the question are giving us 2-methyl 2-butanol. Okay, so what were the options in the question? Option A is 1, 2, and 3. Okay, this will be 1, 2, and 3. Okay, and option B was both 1 and 3. They are not including the reaction 2. C was only 1 and D is only 3. No, what we found, all the three reactions are giving us the same product, 2-methyl 2-butanol. Okay, so the correct answer will be option A, which will be 1, 2, and 3. I hope this is clear. So thus, you can follow the same reaction mechanism pathway, and you can get the same compound as the product just by tuning the reaction conditions a little here and there. Okay, so let us move to the second question of today's tutorial. This is also a question from the topic alcohols. In the reaction given below, you are given here butene, uh, and you are treating carbon monoxide in presence of hydrogen, and this organometallic compound we are treating with this reaction medium, and we are also heating the reaction mixture. That will be the first step of the reaction given. Okay, and then whatever will be formed in the first step, you are asked to treat that intermediate product with copper zinc in presence of hydrogen. So you can clearly understand the second step is basically reduction. Okay, so you just have to identify now that what is being formed in the first step, that and you have to reduce the product obtained in the first step. Okay, so what will happen, let us look at the reaction pathway, what is it following. Okay, so this is a well known process for the formation of aldehydes. Okay, in organometallic chemistry, or you can call in inorganic synthesis, this reaction is a well known reaction for the synthesis of aldehyde. And in their procedure, they treat an alkene with carbon monoxide and hydrogen in presence of this organometallic cobalt complex. Okay, what happens? You get the addition of carbon monoxide and hydrogen across this double bond. Okay, so this product you get in this reaction. In one side, you can simply add carbon monoxide in between the CH bond, and the other side you can visualize as addition of hydride is being happened. Okay, so in the first step you get this aldehyde as the product, and in the second step, which was the reduction step, this aldehyde will get reduced. And what is the reduction product of aldehyde? It is an alcohol. Okay, so you are doing hydrogenation of the aldehyde to give this primary alcohol as the final product. Okay, because we get primary alcohol as the reduction product of aldehyde. So you can see another procedure for the synthesis of alcohols. Okay, in fact, it is a well-known procedure for the synthesis of primary alcohols. Okay, so that was the second question of the tutorial. I hope this was clear. Okay, yes. Can you repeat? Okay, okay. I cannot recall really at this moment, but yes, I think there is a name. But actually, at right now, I do not really recall the name. I'll definitely check and confirm it to you. Okay, is that okay? Yeah, but it is very well known actually. But at this time, since such organometallic reaction steps we do not often follow in the lab, so right now I cannot really recall the name. But yes, I will definitely check and confirm it with you. Okay. So let us move to the next question. What is the major product in the following reaction? So here you are treating this alkene with this mercury compound in presence of water molecule, and in the second step we are doing sodium borohydride reduction on the intermediate product whatever you obtain here. Okay, so the first step will be the oxymercuration demercuration step, whatever we studied in the in the last few tutorials. We have come across this reaction. So in the first step, what happens? You get oxymercuration product on this alkene, which will follow Markovnikov's rule. Okay, and in the second step, the reduction will happen and demercuration step will take place. So let us see how this reaction is being followed. Okay, so what happens? You get a mercuranium ion across this alkene first. Okay, and after getting the mercuranium ion, it will break down to give you a stable carbocation, and then the water molecule will attack at the carbocation to and simultaneously the sodium borohydride reduction takes place to give you the alcohol as the major product. So let us find out in which way you will get the stable carbocation. Okay, so if you get the mercuranium ion across this double bond, you will get the stable carbocation at this position, and you will get OH at this position. And later, demercuration will take place to give you hydrogen at this position. So thus you get the product, which will be this one. Okay. So the reaction is, yes, yes, yes. So thus the reaction is following the uh, oxymercuration demercuration step, followed by uh, and the second step is being carried out in presence of sodium chlorhydride. So let us move to the next question, and this question will be on the topic epoxide. Okay, the most appropriate reagents that can bring about the following transformation is, you are given this cyclopentene and you are asked to treat with these four reaction conditions, and you have to figure out which reaction condition will give you an anti-diol across the double bond. Okay, so if we look at the reaction conditions given here, you will see that KMnO4 in presence of basic conditions will give you an cis diol. Okay, okay. Okay, so KMnO4 in presence of basic condition will give you a cis diol, and when it comes to sulfuric acid followed by heating condition, in this condition as well you get a cis diol. Okay, similarly, option C reaction condition, whatever is given, first you do bromination followed by replacement of a bromide by OH minus, you will get a cis diol in this condition as well. But in option D, whatever reaction condition is given, you are given a per acid. Okay, and per acids are used for epoxidation of carbon-carbon double bonds. So what happens? Per acid will give you an epoxide. Let us consider it as above the plane here. Okay, and epoxide above the plane of this double bond will be formed, and then the oxygen of the epoxide will be protonated by the acid given in the reaction medium, and in the later stage water molecule will open up the epoxide molecule from the below the plane, that is opposite face of the epoxide, to give you this anti-diol. The mechanism has been included in one next question in this tutorial. Okay, and also the mechanism has been discussed in our previous tutorial also. Okay, so we will come across the mechanism in after a few questions. Okay, that question is also has been included. So uh, so the answer will be option D, which will be per acid in presence of acidic medium. Let us move to the next question. Which major organic product is formed in the following reaction? You are treating this alkene with this silver compound in heating condition, and in the next step we are going to treat the intermediate compound whatever is formed with ammonia. So you have to identify which one is the major product obtained in the reaction. Okay. So silver oxide is commonly used for the synthesis of epoxides from alkenes. Okay. So in the first step, you will get the epoxide. And then what happens? The epoxide ring will be opened up by the ammonia present in the reaction medium. So how is it opened? First, the epoxide will form here, and ammonia will attack uh, from the side C. You have two possibilities across this double bond. This is one, and this is the other. So when you treat the epoxide with ammonia, that will attack on the epoxide ring from the less steric side, from through the side where steric hindrance is less. Okay, so that will be definitely this one, because here you have a methyl substituent also. Okay, if it cannot attack from this side because you have a methyl substituent here also. So the epoxide ring will be attacked towards this side, and in turn the arrow will be pushed towards the epoxide oxygen, which will be neutralized in the workup step, and you end up getting NH2 here and OH linked at this position. And you must note down that the attack of ammonia molecule will take place from below the plane if the epoxide ring is above the plane, and vice versa. If the epoxide ring is below the plane, the ammonia molecule will attack from above the plane. Okay, so you end up getting the NH2 and OH functional groups in a and in an anti fashion. So if you look at the products now, option 3, where NH2 functional group is linked at the less steric position, and the OH is pushed to below the plane, that is amine and hydroxyl are lying in an anti fashion. So option C will be the correct answer. Okay, so let us move to the next question. You have to find out what is the major product formed in the given reaction. Okay, you are given the ketone, and you have to treat this ketone with diazomethane in heating condition, and the intermediate product whatever you get in the first step is treated with ethanol in acidic medium. Okay, so let us look at the reaction pathway, how it is going through. When you treat a ketone with diazomethane in heating condition, this is a process used to synthesize epoxides. Okay, so you get this epoxide in the first step. Okay, so this epoxide product whatever we get, when in the second step you treat it with acidic medium, what happens, this epoxide oxygen will be first protonated to give you oxonium cation. Okay, and then now the ethoxide anion can act as a nucleophile to open up this epoxide ring. And just like the previous question, you have two possibilities this time as well. So but you must note down that in acidic medium, first the epoxide ring will open up before the ethoxide anion attacks. Okay, so since in acidic medium, after getting oxonium, it will try to get neutralized, you will open up this epoxide ring either from this way or this way. Okay, So let us see what kind of carbocations we get after opening up the epoxide ring. In this position, you are getting a tertiary carbocation. Okay, but if we open up the ring from this way, you will get a primary carbocation here. Okay, so definitely this opening of this carbon oxygen bond will be more preferable to achieve at a more stable carbocation. Okay, so after opening up this ring via this side, you get a tertiary carbocation at this position, and in this side you get CH2OH. In the next step, the electrophile, the nucleophile will attack at this carbocation to neutralize it, and in turn you get this compound as the major product. Okay, you have to concentrate on the fact that in the reaction mechanism you must achieve the more stable carbocation, which will be attacked by the nucleophile. Okay, so here the tertiary carbocation is preferably being formed. So the this will be the major product, which is option B. Okay. So in the next question, you are given this reaction. In the reaction given below, you are treating cis 3 hexene with this per acid, where you are getting X as the major product, and in the subsequent step we are treating whatever X product we are getting with sulfuric acid in water. Okay, and this gives the compound Y. So the correct deduction concerning X and Y is, you have to first identify X and Y, and then you have to identify what are the what is the relationship between x and y. Okay, so like you have to identify whether x is meso and y is meso, or is x is racemic mixture or y is racemic mixture. You have to identify the stereo chemistry of the product x and the product y. Okay, so let us see how the reaction is being followed. When you treat this alkene with per acid, this epoxide you get in the reaction. Okay, and the reaction mechanism was discussed in our previous tutorial. So this epoxide is being formed, but you cannot know whether the epoxide is being formed above the plane or below the plane. So the product X which you are getting in the first step is a meso product. Okay, and subsequently, when you treat this epoxide with sulfuric acid, since the alkene is a symmetric alkene, this time whatever carbocations are being formed during the opening up step of epoxide, you get the same outcome only. Okay, so you can either uh, after breaking up the epoxide being formed, whether it is on above the plane or below the plane, you get mixture of enantiomers. Okay, so mixture of possible enantiomers will be present in the reaction medium after the second step. So in turn, you will get a racemic mixture as the product. Okay, like for example, if you try to note down the RS configurations of these two uh, stereogenic centers, you will get either RRSS or RSSR in enantiomeric mixture like that. So in turn, you get a racemic mixture in the second step of epoxide opening. Okay, so thus we found that X mixture will be a meso mixture, while Y1 will be a racemic one. Okay, so here option B will be the correct answer. Now let us move to the next question. The reagent that can bring about the following transformation in good yield is or are. Again, we are synthesizing this antidiol from a from this cyclohexene molecule. Okay, and you are given three reaction conditions, and you have to figure out which of the reaction conditions will give you this antidiol. Let us look at the first option. It is given the condition for ozonolysis. Okay, so what happens when we subject an alkene to ozonolysis? We get a if it is a acyclic molecule, you end up getting two carbonyl compounds as the major product, and if it is a alicyclic molecule, you get a dicarbonyl compound as the product. Okay, so if we subject cyclohexene to ozonolysis conditions, this this carbon-carbon double bond will undergo oxidative cleavage, and you will get 2 aldehyde functionality in this position. Okay, at this carbon you will get aldehyde functional group, and this carbon as well you will get a carbonyl group, that is aldehydic functional group here, and this carbon carbon double bond will be broken by oxidative cleavage. So you will not get this antidiol for the first reaction condition. Now let us move to the second reaction conditions. We already talked that KMNO4 in basic medium gives us a cis diol. Okay, how the reaction mechanism is followed in this way. First, the manganate will coordinate with the carbon-carbon double bond to give you this five-membered intermediate. Okay, and this five-membered ring containing intermediate is opened up by sodium hydroxide, giving you the cis diol. Since this manganate ion is coordinating from the same face of the molecule, so the hydroxide ions open up the five-membered ring containing intermediate product, and you end up getting diols at these two positions. So the product obtained in this step is a cis diol. Okay, thus condition B is also giving us a cis diol. And when it comes to condition reaction condition C, we are treating the cyclohexene molecule with this per acid in water medium, and under heating condition we get an epoxide first, which upon boiling with water will be opened up to give you an anti-diol. How? So this is the reaction mechanism that it is following. Okay, well, if the first step has been discussed already in the previous tutorial, like this you get a epoxide. Okay, this double bond attacks at this oxygen atom of the per acid. In turn, the arrows are pushed towards this nucleophilic carbonyl of the per acid, and this carbon oxygen double bond extracts this proton, and this OH bond is cleaved. Thus, This oxygen atom is overall transferred to the carbon carbon double bond to furnish this epoxide. Okay, and then in the subsequent step of this option 3 reaction condition, what happens, since we are doing it in water medium, this epoxide oxygen atom is first protonated to give you this oxonium ion. Okay, and subsequently this three membered oxonium is opened up, giving you the more stable carbocation, and the more stable carbocation in the next step is attacked by water molecule in this way, and in the work up step you end up getting this NT-diol as the major product. Okay, this molecule attacks at the epoxide ring from the opposite face of the compound. Thus, we found that among these three reaction conditions, only option C is giving you the desired anti-diol. Okay, so yes, okay. So let us move to the next question. Consider the reaction given below, where you are treating this enantiomercury pure epoxide with this thiol in acidic condition. So you have to find out what is the major product formed in the reaction. Also, you have to find out whether a single enantiomer is formed or a racemic mixture of the product is obtained. Okay. Out of these four options, two options will be correct this time. Okay, one will be the major product formed, and also you have to comment on the stereo chemistry of the product obtained, whether it is a single enantiomer or a racemic mixture is obtained. So we have already talked about opening up of epoxide rings. What happens in acidic medium? First, it will be protonated to give you oxonium, and then this ring will be opened up via this way, and you get a carbocation here, and this carbocation is attacked at this position via the thiol molecule in the reaction medium. So this is the mechanism that the reaction is following. This is suppose the enantiomerically pure epoxide what we are reacting, and in presence of acid this oxonium you obtain, and then subsequently you get a carbocation center here, and this carbocation center will be attacked by this nucleophilic sulfur compound. Okay, and you get this thio compound as the major product. You must note down that the product obtained in this reaction will be a single enantiomeric compound. Okay, because we are beginning with an single enantiomer, and the, if it is a single enantiomer, there is only one possibility of attacking the carbocation of this compound, which will be opposite via the opposite face of the epoxide ring on this compound. Okay, so only one possibility is there, and in turn you get only one single enantiomer as the major product. So out of these four options, you will get to see that this is the product you are obtaining in the reaction, And also option C will be the correct one. The product would be a single enantiomer. So B and C are the correct options for the reaction. So I hope it is clear. Let us look at the next question now. What would be formed if 2-phenyloxyrane is treated with methyl magnesium bromide followed by acid hydrolysis? A similar question is also here on epoxide opening. You are given this phenyloxyrane and you are treating it with methyl magnesium bromide followed by acid hydrolysis. Okay, so what happens? The similar mechanism will be followed here, and you will get first the protonation of this oxygen atom will happen, and the opening of the three membered intermediate will take place, and you will get the stable carbocation at this position. I remember in one of the previous questions, I think I mistakenly said we will come to that at the end, but here we will see that you will get the stable carbocation at this position, and we are going to open up the ring via this carbon oxygen bond. Okay, and in the subsequent step, okay, okay, in this question, see, at first we are treating with methyl magnesium bromide, not adding the acid first. Okay, so what happens? First, the opening of the epoxide ring takes place, okay, by the methyl magnesium bromide. So oxonium will not form at the first step. Okay, so here there is no picture of carbocation comes. Okay, in presence of acid in the medium only we get the oxonium here, but in the reaction medium here we are adding acid later. Okay, so first the opening of the epoxide ring by methyl anion will take place, and that will be carried out from the less less statically hindered side. Okay, so methyl will attack at this position. Okay, and this epoxide ring will be opened up from this way. So in turn you get pH here and OH linked here, and methyl will be linked here. Okay, so after opening first you get O minus here, and since you are adding acid in the medium, like in the workup step, the O minus will pick up a proton and you will get OH linked at this position. So this will be the product obtained in the reaction. Okay, you always need to remember that epoxide ring opening can be carried out in via two mechanisms. One, by addition of acid first, and the second one, addition of acid at the late stage. So if we add acid in the first stage, you will get the oxonium first before the nucleophile attacks. But if we are not adding the acid first, the nucleophile attacks first from the less statically hindered side. So in this reaction, you get this product as the major one. So option A is the correct answer. And let us move to the next question. So this question onwards, the questions will be on the topic of aromaticity. Okay, arrange the following compounds in increasing order of polarity. Okay, so three carbonyl compounds are given here. which and all of which are alicyclic. Okay, so you have to rank them in in increasing order in terms of polarity. Okay, definitely all these three alicyclic molecules are containing oxygen molecules which will try to push electron pairs from the ring systems. But how we will rank them in terms of polarity, let us see. In this three membered ring carbonyl compound, what happened, this uh, carbon oxygen double bond, in this bond the electron pairs shared between carbon and oxygen will be moved towards the more electronegative oxygen atom. Okay, so the electron density is moved towards this oxygen atom of the carbonyl compound, and in turn the compound becomes polar. Okay, and the dipole moment will be oriented towards this carbon oxygen double bond side. Okay, so this compound is polar. Now let us move to the second molecule. In the similar way, if we try to move the shared oxygen pair towards this oxygen atom, more electronegative oxygen atom, what we get in turn, we can visualize this carbon oxygen double bond as O minus here and C plus, that is a carbocation species here. But the carbocation species, whatever we generate by by moving the shared electron pairs towards the oxygen atom, we end up getting a anti-aromatic system in this ring. Because this when it comes to aromaticity rule, that is 2n plus 2, if we follow that, you will end up getting an anti-aromatic system for this five membered ring, which will be having 4 pi electrons. Okay, so this anti-aromatic system will lead to a highly unstable system for this second compound. So we cannot say that this shared electron pair of this carbon oxygen double bond can be pushed to the oxygen atom completely, like we did in the first compound. Okay, so we cannot do that. Rather, this double bond will remain intact, so that this cannot impart anti-aromaticity to this five membered ring. Okay, so that will lead to a lower polarity of this compound, because this time dipole moment will not be completely oriented towards this carbon oxygen double bond, so polarity for compound 2 will be less. Now, yes, 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 that is what, yes, that is what we, yes, actually we cannot push the shared electron pairs towards the oxygen for this compound, because that will lead to the formation of this anti-aromatic system here. Rather, this oxygen pair will participate with this ring also. Okay, is it clear? Yes, yes. Otherwise, you will get a positive charge here, which will lead to anti-aromatic system. So we cannot give the shared electron pairs totally to the oxygen. Hence, the polarity of this compound 2 is lowered, because it is not totally oriented towards the oxygen atom. Now let us move to the third compound given. Okay, here what will happen if we give the shared oxygen pair of the CO double bond to the oxygen atom? What happens? In turn, you get an O minus here and a carbocation at this position. Okay, you get a CO single bond and you get O minus here and C plus here if we give the shared electron pairs to the oxygen atom. Okay, and then you get a positive charge here, and if you look at the cyclic framework of the compound, now you have a 2n plus 2 electrons for the three membered ring. So the ring becomes aromatic. Okay, and a system which will attain aromaticity by sharing this electron pair in this way will definitely favor this process. Okay, this ring will prefer a positive charge at this carbon atom and a negative charge on this oxygen atom because the system is attaining higher stability by aromaticity. Okay, so definitely this compound 3, in this compound 3 you can totally give up the shared electron pair of this CO double bond towards oxygen, visualizing it as an O minus ion and placing a positive charge here. Okay, so thus the compound 3 will be highly polar since the the shared electron pair is completely given up to the oxygen atom to make it O minus, and the dipole moment will be oriented towards the upside. Thus what we found that compound 2 will be the least polar, followed by compound 1, where we did not have any issue in moving the shared electron pairs towards oxygen, and the most polar compound among all three will be this third one. Okay, because here the moving of the shared electron pairs towards oxygen is further favored by the presence of this double bond, since we are getting an aromatic system at the end. So the order of polarity will be followed in the way which option C is depicted. Yes. So thus here the description is given. You can take a note or maybe a screenshot of the explanation, which will help you understanding the ranking. Okay, how what process we carried out and why compound 2, in compound 2 we could not do the same process. Okay, so option C is the correct answer. Let us move to the next question on the topic aromaticity. In principle, what is true regarding benzene and 135 cyclohexatriene? So 135 cyclohexatriene is an imaginary compound. Okay, it is basically the cyclohexane ring which contains three double bonds inside the ring. Okay, and no question of uh, conjugation, no question of delocalization of electron pairs comes in this imaginary compound. It is simply the cyclohexane which contains three individual double bonds. Okay, so you are being asked in principle what is true regarding benzene and 135 cyclohexatriene. Definitely these two compounds may look alike, but they are not chemically or physically as well same. Okay, so let us look at the options given. Theoretically they are the same molecules. Option B, both have same lengths of all of their CC bonds. Then both have same enthalpy of hydrogenation, and cyclohexatriene has three different carbon carbon single bond lengths while benzene has only one type of carbon carbon bond length. Okay, so these four options are given. You have to figure out which statement is correct regarding benzene versus 135 cyclohexatriene. Are they theoretically? Yes. No, that is actually a theoretical molecule, 135 cyclohexatriene, that hasn't been synthesized yet, but it is just a hypothetical molecule. And in principle, if you try to look at a similar kind of molecule, you will end up getting benzene only, because you get delocalization across the ring. Okay, so you cannot in principle be able to get 135 cyclohexatriene. Okay, because always the delocalization of pi electrons across the six membered ring will take place. Okay, so 135 yes, 135 cyclohexatriene will be the hypothetical molecule only. So they cannot be theoretically the same molecules. And when it comes to enthalpy of hydrogenation, since both the molecules are different, enthalpy of hydrogenation will also be different. But the major difference that comes in between these two molecules is actually the carbon carbon bond lengths. Okay, like I said, in cyclohexatriene, you get no question or no picture of delocalization of pi cloud. You just simply get carbon carbon single bond, followed by carbon carbon double bond, uh, then followed by another carbon carbon single bond. So you get distinct carbon carbon single bonds and carbon carbon double bonds and carbon hydrogen single bonds. You get distinct single and double bonds in cyclohexatriene, whose bond lengths remain constant. Okay, whatever the universal value of CC single bond and CC double bonds, that will remain intact in cyclohexatriene. But when it comes to benzene carbon carbon bonds, you get all the carbon carbon bond lengths same, which whose lengths will be between carbon carbon single and carbon carbon double bonds, because due to delocalization of pi cloud across the system, all the carbon atoms of benzene ring will behave exactly similarly. Okay, and you end up getting a a complete conjugation across the ring, and you get all the carbon carbon bond lengths same. So thus all the both the compounds cannot have the same lengths of their carbon carbon bonds. So for this question, this for this particular question, option D will be the correct answer. This is the explanation, which has also showed the carbon carbon single and double bond lengths in the hypothetical compound 135 cyclohexatriene. Okay, so option D will be the correct answer. Now let us move to the next question. Select the species which is not aromatic. You are given these four compounds, and all these compounds are possessing a five membered unsaturated ring, which are containing heteroatom in it, and you have to identify which of these following compounds is not aromatic. Let us look at these one by one. The first compound given, which is a pyrrole, You have these double bonds, carbon carbon double bonds here, and a lone pair on this nitrogen atom. Okay, so if you try to count the number of pi electrons for this pyrrole molecule, you will see that 1, 2, 3, 4, and 2 electrons from the lone pair of nitrogen atom. In total, 6 pi electrons are moving, that is delocalizing across this 5-membered ring. Okay, so if you have 6 number of electrons, that is 4n plus 2, where for here 2 n will be n is will equal to 1. So if you have 4n plus 2 electrons in the system, you have this pyrrole molecule to be aromatic. Okay, so option A can be excluded now. Let us move to option B, which is a furan molecule given. So in furan also, one of the two lone pairs of oxygen atom participate in the delocalization of pi electrons across the 5-membered ring, and you get total 6 pi electrons for the furan molecule as well. Okay, so you have 1, 2, 3, 4, 5, 6, 2 from the lone pair of electrons. So you have furan also possessing 4n plus 2 electrons, and in turn it is an aromatic compound. Now let us come to option C, which is the boron containing 5-membered ring. So what happens? Boron is not having any lone pair to donate. Okay, all the 3 valence electrons for boron are participating in formation of bonds in this compound, and no lone pair of electron is being possessed by boron, which can be donated to the ring, so that you get delocalization of pi electron across the ring, and thus this compound is having only 4 n pi electron. And what happens if you have 4 n number of pi electrons? You get an anti-aromatic compound, isn't it? So thus option C, boron compound, is not aromatic. Okay, and then if you look at the option D, which is a substituted pyrrole, here also you have lone pair of electrons in the nitrogen atom. So those lone pairs, that lone pair will be donated to the ring, and total 6 pi electrons will delocalize across the ring, and you can visualize the delocalization of pi electrons in this fashion. So uh, among all the 4 options given, the compound C is not the aromatic one, rather it is anti-aromatic. Okay, so option C will be correct for this question. Now let us move to the next question. Consider the following bromides. You are given 2 alicyclic bromides, and you have to comment on the decomposition of both the bromine containing compounds here. Okay, so the options given are: both decomposes to form Br minus, that is bromide anion; both decomposes to form this bromine with a positive charge; or compound 1 decomposes to give anion and 2 gives cation; or 1 decomposes to give cation while 2 decomposes to give anion. Okay, so you have to first identify the mechanism that these 2 compounds will follow to undergo decomposition and liberate anion versus cation. So let us look at the first compound. Okay, what happens if you break the carbon bromine bond? You will get a positive charge and a negative charge. Now you have to figure out to which species you will give a positive charge and to the other you will give negative charge. Suppose we are giving the positive charge to this carbon atom of this 5-membered ring after breaking the carbon bromine bond. Let us imagine that we are giving positive charge here and negative charge to the bromide. So if we give positive charge to the ring, we are getting a highly destabilized anti-aromatic system because you have 4n number of pi electrons. So you now know that you cannot break this carbon bromine bond in this fashion where we are giving the minus charge to the bromine. Rather, you will have to eliminate the bromide cation from this compound, which will give you a negative charge at this carbon atom. Okay, so if we eliminate the bromide cation from this compound, you will get a negative charge here, and in turn you get 1 2 3 4 and 2 electrons from the minus charge. In total 6 electrons, which will be 4 n plus 2 number of electrons, and those 4 n plus 2 will give you a highly stable aromatic system. So you get cyclopentadienyl anion and bromide cation from the first compound. I hope that was clear. So when it comes to the next compound, let us see how we are going to break the carbon bromine bond for this compound. Okay, here we gave minus charge here. So in the next compound where we will give the minus charge, let us see. Suppose we are giving the minus charge to this ring, just like we did for the compound one. So if we give the minus charge to the ring and the positive charge to the bromine, what happens? You have now 8 number of pi electrons oriented on this ring. Okay, 1 2 3 4 5 6 7 8. 8 number of pi electrons are delocalizing across the 7-membered ring, which will lead to a destabilized anti-aromatic system. So, breaking of this carbon bromide bond in this fashion will not be favorable, while the breaking will be favorable only if you get a positive charge at this position. Okay, because what happens if you put the positive charge here, you have 6 pi electrons delocalizing across the system, which will lead to the formation of a aromatic system. So here you cannot eliminate Br plus, rather you have to eliminate Br minus in this system. Okay, so this is the complete explanation written down here. What happens in compound 1, Br will dispatch as Br plus, like we said, so that it gives a number of 6 pi electrons across the ring. And on the other hand, in compound 2, Br will dispatch as Br minus, so that you get total 6 number of electrons on this 7-membered ring. I hope this is clear. Okay, so if it comes to option, the correct option among these, we clearly know now that 1 decomposes to give Br plus, while 2 gives Br minus. So option D will be the correct answer. Let us now move to the next question. The following compound, when treated with excess of AgBF4, silver tetrafluoroborate gives a red precipitate, leaving a highly conducting filtrate due to. So, in the system, we are running this reaction where this cyclobutene framework is being subjected to reaction with the silver compound, which is giving you a red precipitate, and the reaction mixture is a conducting solution. That means it is possessing ions in the system. So, which statement regarding the reaction given here is correct? Option A, a dianion aromatic system is formed. Option B, a dication aromatic system is formed. Option C, a covalent ditetrafluoroborate compound is formed. Option D, an aromatic salt precipitate which is red color. So, first of all, you have to now try to identify which product you will get if you treat this compound with silver tetrafluoroborate. Silver will first extract the bromines. So let us first remove one bromine atom from the starting material. What happens here? You get a positive charge here, uh, or maybe negative. Let us first consider the case where you get a positive charge here. Okay, so you get conjugation of this bond across these three carbon atoms. Okay, now if we remove the second bromine, you get a positive charge here, and you have a dication system, cationic system, with 2 pi electrons in the ring. So thus you have a 4n plus 2 system, which is containing 4n plus 2 pi electrons, and you have a dicationic species here. So due to the formation of aromatic system, definitely this process where we are giving positive charge to the ring for both the times when we remove the bromine is favorable. What will happen if we consider the dianionic species? We will have first a an anion generated here if we remove the bromine as Br plus, but you will get a 4 and 4 and pi system across these three carbon atoms, and after you form this anionic charge here, formation of the second anionic charge will be highly unfavorable due to electron repulsion. Okay, so due to the electronic pair repulsions, this dianionic species formation is not possible. And anyway, in the process when we were generating the dicationic species, after eliminating the bromine as Br minus, we were getting an aromatic system. Okay, so for this particular question, option B will be the correct answer, where you are getting the dicationic species, because the aromatic dicationic is formed and the number of electrons become 2, which will obey the 4n plus 2 rule. Okay, so the option B will be the correct answer, leading to the formation of stable aromatic compound. Now let us move to the next question on the topic of aromaticity. When potassium metal is added to 1357 cyclooctatetraene, a highly conducting salt is formed without evolution of hydrogen gas, because which of these four pathway is followed in the reaction. Thus, the starting material is reduced to give you this anionic species, or is the starting material is being reduced to give you dianionic species, or reduction of cyclooctatetraene into C8H10 is being formed, or you get this dicationic species you have to identify. Okay, what happens when we add potassium metal to 1357 cyclooctatetraene? So what happens in the process? Potassium metal donates its electron to achieve octet, and it forms an ionic species here. Okay, so in the process, the cyclooctatetraene molecule takes up electrons from two potassium atoms to give you this dianionic species. And in this dianionic species, if you count the number of electrons, you have 1, 2, 3, 4, 5, 6, 7, 8, and 2 electrons from the proton. So you have 10 number of electrons. So it is following the 4n plus 2 rule of aromaticity, and since the product that is being formed is aromatic, you will get this dianionic species. Okay, so thus the option B will be the correct answer. You get C8H at 2 with 2 negative charges. Uh, yes, yes. Okay, okay. So your question is where we are locating the two extra electrons on this ring, isn't it? Yes. The two electrons will be across the ring. You cannot particularly locate it to a particular carbon atom. It will be these two extra electrons will present in the electron cloud of this ring, which will delocalize across the ring along all the carbon atoms of the ring. Okay, you cannot particularly locate these two electrons to one individual carbon atom. Okay, that will delocalize across the ring. Okay, so that will be present in the whole, yes, in the whole ring overall. So, and after getting the two extra electron, these double bonds will also not be located at their respective positions. Okay, now all the pi electrons, the 10 number of pi electrons which will be present, since they are attaining aromaticity after addition of two extra electrons, all the 10 pi electrons now will move across all these 8 number of carbon atoms. So this system now becomes aromatic, and the electrons will delocalize across the ring. So thus option B will be the correct answer for this question. Now let us move to the next question. So Pyrene, although aromatic, decolorizes brown color of bromine water. So now you are given another statement regarding the pyrene molecule. It has one pi bond extra, which is not part of the aromatic system. So you are now given four options regarding the two statements given about the pyrene ring. Okay, maybe the statements, maybe both the statements are correct, or maybe one of the statements are correct, or maybe both the statements are incorrect. Okay, you have to figure out that. But these two statements are given that this pyrene molecule is aromatic, but it decolorizes the brown color of bromine water. That means which indicates the presence of extra unsaturation bond. Okay, so and the second statement is it has one pi bond extra, which is not part of the aromatic system. So now let us read the comments give based on these two statements. Both statement 1 and statement 2 are correct, and statement 2 is the correct explanation of 1. Both statement 1 and 2 are correct, and 2 is not the correct explanation of 1. Statement 1 is correct, but statement 2 is incorrect. Statement 1 is incorrect, but statement 2 is correct. So, what happens in case of pyrene? Yes, this is an aromatic system, but one double bond in the pyrene molecule, which is this one, does not participate in aromaticity. Okay, the pi bonds located in these three rings. Okay, not this one. Actually, in the course of delocalization of pi electrons, you will end up getting a carbon-carbon double bond at this located at this position, and in that particular structure all the rings will have delocalization of electrons, but in that particular structure this middle carbon carbon double bond will not interact in aromaticity, will not participate in aromaticity. In turn, that carbon carbon double bond will remain isolated, and that with that double bond which is not participating in aromaticity will be available to react with bromine water. So here the explanation is given. Pyrenes are strong electron donor materials and has one pi bond extra, which is not the part of aromatic system. Thus, it decolorizes brown color of bromine water, and hence option A is correct, which is saying both statement 1 and 2 are correct, and statement 2 is the correct explanation of statement 1. So yes, this pyrene molecule has an extra carbon-carbon double bond which is not participating in aromaticity, in turn which decolorizes the brown color of bromine water. So option A is the correct answer for the question. Next, you have this question. The following compound is optically active. So this polycyclic molecule is given to you, regarding which another statement is given. It has a chiral carbon. So now let us read the comments regarding the statements given. Okay, both statement 1 and statement 2 are correct, and statement 2 is the correct explanation of 1. Option B, both statement 1 and statement 2 are correct, and statement 2 is not the correct explanation of statement 1. Statement 1 is correct, but statement 2 is incorrect. Statement 1 is incorrect, but statement 2 is correct. So, this polycyclic molecule, this kind of compounds are optically active, but they do not possess any chiral center or chiral axis. But then, how is it possible to call these compounds as optically active? Actually, although it is drawn in a planar fashion, these molecules in actual in 3D, they lie in this fashion where the molecule possesses a helical shape or helical structure. Okay, you can visualize these molecule as such helical structure, and hence these molecule being non-planar attain asymmetry in the structure of itself. Okay, so these compounds are optically active. If you look at the mirror image of these compounds, you will get to know that these compounds are non superimposable mirror images. Okay, so this compound will have this mirror image as its enantiomer. So this compound is optically active, but due to its structure or its shape being, maybe you can call geometry, its geometry being helical, this compound is possessing chirality, and this phenomenon is basically called as helical chirality. The molecules which show helical chirality do not possess any chiral carbon or any chiral axis. Rather, its geometry imparts the chirality to the molecule. Okay, so for the compound given, you will see that yes, the compound is optically active, but it doesn't have a chiral carbon. So statement 1 is correct, but statement 2 is incorrect. Okay, so for this particular question, option C will be the correct answer. So with this, we have discussed the few questions on the topics alcohols, epoxides, and aromaticity. So let us quickly go through the questions discussed in the tutorial. So we started the question series with this question where you were asked to identify the reaction condition which would give you 2-methyl 2-butanol as the major product, and we found that all the three reaction conditions were giving you the desired product. Okay, okay, so we saw that all the three reaction conditions were giving you the desired product. Then we moved to this question where we first synthesized an aldehyde by using this cobalt metal complex, and in the subsequent step we reduced the product obtained in the first step to get this alcohol as the major product. And in the next question we found that this alkene was subjected to oxymercuration demercuration condition, and in the process the more stable carbocation was formed, then which was then neutralized by water molecule, and demercuration step took place with sodium borohydride. Okay, and then we saw this question where you were given various conditions and you were asked to identify which condition was giving you the anti-diol, and we saw that the epoxidation reaction condition followed by acid hydrolysis gave us anti-vicinal diols. In the next question, we treated this alkene with silver oxide, where we saw that the incoming amine and the newly introduced hydroxy functionality were lying in anti-fashion in the final product. In the next question, we first synthesized epoxide from this ketone using diazomethane, and we opened up the epoxide ring in presence of ethanol. Okay, and in the next reaction, we treated this alkene with alkene with peracid to get an epoxide, which was further subjected to acid hydrolysis, and we saw how in the first step we get meso product, but in the final step where we opened up the epoxide ring from the opposite face, we got a racemic mixture. Then we came across three reaction conditions, and we were asked to identify which reaction condition was giving us anti-diol. And like we discussed in one of the previous questions, the epoxidation condition was giving us the anti-diol. And then we saw how this epoxide was giving us our desired product when we treated it with this thiol in presence of acid. And like the previous questions discussed here as well, we obtained the more stable carbocation here, which was followed by attack of thiol. Then we reacted 2-methyl oxirane with methyl magnesium bromide, and we also discussed how the epoxides are opened in different ways in presence and in absence of acid substance. So here, in absence of acid substance, we opened up the epoxide ring with methyl magnesium bromide, and subsequently we obtained this alcohol as the product. And then we moved to the topic aromaticity, and we talked how the dipole moments in these three compounds were oriented in their particular directions, and we ranked them in increasing order of their polarity. Okay, and their polarity dependent were solely dependent on the aromaticity that the ring was going to obtain after we move the shared electron pair of carbon oxygen double bond towards oxygen versus towards carbon. Okay, so we ranked them as their increasing order of polarity. We also found the difference between the hypothetical compound 135 cyclohexatriene versus benzene, and we talked how the compound 135 cyclohexatriene contained three different types of single and double bonds. Okay, rather in benzene we talked how we get only one kind of carbon carbon bond. Then we talked about the aromaticities of A, B, and D compounds, and we saw how in C, due to the absence of lone pair of electrons in boron, the compound was not aromatic. Then in the next question, we talked about cleavage of carbon bromine bond in compound 1 and 2, and we discussed how to break these bonds and which species to look which species to be given positive and negative charges. Okay, and that process is completely depended on the aromaticity that was obtained by by this ring after carbon bromine bond cleavage. Okay, so in the next question we saw how this conducting reaction solution was carried out, and we saw that due to aromatic to achieve aromaticity, this compound was decomposed to get a dicationic aromatic system in this reaction. Okay, and in the next question we saw when potassium metal was added to this 1357 cyclooctatetraene, we got a species which is C8H82 minus, which was an aromatic system possessing 10 pi electrons. And then we talked about pyrene, how despite its being aromatic, one particular carbon-carbon double bond was not participating in the aromaticity, and that was decolorizing the brown color of bromine water. And lastly, we talked about helical chirality of these kind of systems, which do not possess any chiral carbon on it, and do not possess any chiral axis, but due to its helical geometry, it becomes stereogenically active, and they possess an enantiomeric in this fashion. Okay, so with this we have come to the end of this. Yes, this one. uh, Previous year questions. Hello. Okay, like on this topic. Okay, actually in last year there must be some different TA which who took this course for this topic, but I will try to search for for these questions, and I will try to ask for more questions from those TA whoever taught in last year, and I will try to provide it to you. Is that okay? Yes. And yes, do you have access to the public sheet where we share the slide presentation, PowerPoint presentations, and we share the YouTube video links? Do you have access to that public sheet? No, right? Okay, then. Okay, what will be the way to share the questions then to you? Uh, Maybe you can share your email ID at the chat box. Okay, is that okay? Yeah, please share your email ID at the chat box. I will send the PDFs of previous questions or more questions on the topics with you via email. Okay, so you just drop your email ID there, because if you do not have access to the public sheet, I thought you have the access, but if you do not have the access, then there will be no other ways to share the question papers with you. Okay, so please share the email ID. Also, I will clarify the whatever name reaction that you asked in today's lecture. I will clarify that via mail. Okay, is that okay? Since this is the last tutorial for the course. Okay, thank you very much. I will just quickly take a screenshot. Okay, so fine. I will share the question papers, whatever, or maybe materials also for this course. I will share with you via email, and whatever doubts or questions that arose in today's lecture, I will clarify it with you. So thank you for joining. So I will get back to you. Thank you.